Good day and welcome to the Geo-Institute 4th Annual Live Streaming Web Conference. Today's topic will be Sustainability in Geotechnical, and the program facilitator is Bhaskar Chittoori. This is an audio web conference. You will hear the presentation through your computer speakers, and there will be a PowerPoint presentation that will be shown throughout the meeting. You can ask a question through the online web conference tool at any point during the session by clicking on the Ask Question button on the left of your screen. Type your question into the box and hit the Send button to submit your question. I'd now like to turn the floor over to today's facilitator, Bhaskar Chittoori. Sir, the floor is yours.
Thank you so much, David. Hello, everyone. Welcome to the Sustainability in Geotechnical Engineering session for the Web Conference 2019, hosted by Geo-Institute. In today's session, we are going to talk about different aspects of sustainability in geotechnical engineering. And we have a variety of frameworks that we are going to talk about. And the presentations include a unified sustainability and resiliency assessment framework developed for evaluating pavement infrastructure and earthen dams, and demonstration of connection of geotechnical project to sustainability through the ENVISION sustainability rating system. In addition, there is also a case study which highlights the heat extraction from municipal solid waste landfill. So all these presentations will give you some insights into how sustainability in geotechnical engineering is progressing. And today's session is sponsored by Keller, which is a gold sponsor. Keller Foundations, the companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide, including all services in one contract. Keller reduces client risk and ensure all aspects of project are met on time and on budget. So we thank Keller for being sponsoring this session. So there are basically 4 different presentations in today's session. The first one is going to be by Dr. Jeff Keaton, who specializes in quantifying hazardous natural process for siting and design of all types of facilities in geologic environments, and is particularly interested in quantifying uncertainty and variability in geologic observation and characterizations. He has degrees in geological engineering, geotechnical engineering, geology, and from the University of Arizona, UCLA, and Texas A&M, and is licensed as an engineer and as a geologist. Keaton has been employed by consulting firms for over 45 years, and in Wood's Los Angeles office since 2005, where he is a principal. He serves on editorial boards of Engineering Sustainability Journal, Quarterly Journal of Engineering Geology and Hydrogeology, Bulletin of Engineering Geology, and various other journals. He is the past president and honorary member of the Association of Environmental and Engineering Geologists, and fellow of the American Society of Civil Engineers and of the Geological Society of America. He is also the past chair of the Sustainability in Geotechnical Engineering Committee. He is also in the Committee on Sustainability, the Steering Committee of Geotechnical Extreme Event Reconnaissance, the GEAR Association, and currently serves as the past chair of Engineering Accreditation Commission, ABET, and recently received the ABET Fellow Award. So without any further ado, I give the floor to Dr. Jeff Keaton to start the first presentation for this session.
Very nice. Thank you for that introduction, Bhaskar. Very successfully. The presentation doesn't seem to be, oh, there it is. Getting this under control. Sorry for that rough start. What I am trying to accomplish with the presentation this morning, this initial presentation, is to identify a variety of elements in projects that are geotechnical in nature that demonstrate the breadth of sustainable contributions that we civil engineers are able to make, many of which are not very visible, some of which are very visible. The context I'm going to use in a brief way, because of the time constraints here, is the ENVISION rating system. Many of you, in fact, I would hope by now all of you are familiar with this, or at least aware of it. And so I'm not going to go into the details here because that is rather involved. I will, as a method of introduction here, just say that the principles of sustainable development can be summed up for us engineers in two principles. Doing the right project is one, and doing the project right is where we commonly live. Most of us are in the do the project right mode because we don't set the project. We identify a project that we're invited to participate. And so doing the right project is commonly for new projects, although we do have an opportunity to infuse the right project concept or mentality along the way. There's some complexities there, and if we have a chance, we'll talk about that at the end here. I have a series of slides that really focus the meat of this really on geotechnical project elements that are sustainable in their character, and on a couple of complex projects that really have a sustainable component at their heart. I do want to make a brief comment about underground space utilization in a way that I imagine you're not expecting, but it really extends across the board. And then I want to kind of put out something that I feel strongly about, the idea that green is the color of sustainability, when I think for us engineers purple is a better color. So with that, I'll move into a series of geotechnical projects that have elements, and a few of them that components. That's these first 5, and then the last 2 are really projects themselves that are rather unique, very unique maybe. So here's a highway, a state highway in Oregon that crosses a small stream. It's called Mill Creek. I discovered this in 2008 when I was working on a rock scour at Bridge Foundation's project for the National Cooperative Highway Research Program. And a very interesting aspect about this particular site is siltstone. You can see the photo that has the yellow notebook in it. That's a chunk of siltstone that came from below water. I pulled it out and took pieces of it back for laboratory testing, which I transported in a bucket submerged in water because, as you can see with that small photo on the right, it slakes in air. I mean, it slakes completely in air. The photos were taken 1 month apart, but the evidence of slaking was visible within 15 minutes of being out of water. So if you can read the small text in the overprint on the photo, you see 1945 Bridge Foundation. That was the original construction in 1945 for that 2-lane road. It was improved in 1973. Presumably the reason was traffic capacity. It just needed to have more capacity for safety as well as volume. But the important thing here is that in 1973, somehow the decision was made to incorporate the 1945 foundation as part of the 1973 foundation. Now, I think we would all consider that, certainly the old-timers, of which I am one now, would consider that to be just good engineering. But I think the idea for us to accept that as good engineering can be embellished as we try to communicate the sustainability in geotechnical engineering as something that we're striving to make happen, not allowing to happen in the background under a name that doesn't give it the recognition that we would like to have it receive. So here's the checklist. Very tiny words. I'm not going to comment about much of these things. Let me make a quick shift here on my own screen. So this is providing, what you see there is provide effective leadership and a decision to make something sustainable, even though it wasn't called that in the at the time it was done. But nonetheless, it's definitely falls under that category in the ENVISION rating system. Mexico City has a very interesting geologic condition that results in consolidation of soft clays as groundwater resources lower the groundwater level. And that is a problem. The soft clays create a problem not only for building support, which requires piles, although that's a common foundation type, but the groundwater decline is causing subsidence. And the problem with a combination of groundwater-induced subsidence and pile-founded buildings is that if the potential for the ground level of the building to become elevated relative to the ground that has all kinds of challenges, utility connections and entries and so forth. So the example here is in the western part of Mexico City, the Polanco area. It's the headquarters building of A.M.ASCE. And we could get into a discussion about sustainability with an oil company context. But here's an example of the situation. The photo on the left is the Angel of Independence statue on a column at Paseo de la Reforma, and that is a pile-founded monument. So that it was heavy enough that they didn't want it to settle because of the compressibility, so it's on piles. And 1910 to 1950, the lower right, well, before the 1950 photo on the right, lower right, you can see in the middle, that tiny photo, some deformation of the concrete slabs around the base of the statue, the monument. So by 1950, 1.8 meters of subsidence had occurred, and that was dealt with a series of steps for that monument. By 2012, when the upper right photograph was taken, the ground subsidence of 3.2 meters had occurred at that location. So here's a building on the left, apartments it looks like, maybe retail at the bottom. And the Basilica de Nuestra Senora de Guadalupe on the right. And that was built, constructed 1974 to 1976. A very heavy building with shallow foundations. And you can see the subsidence, which was corrected, and I'm not sure how it was done, but maybe Hayward Baker had our sponsor, one of our sponsors may have been involved in correcting that problem. So you can see the challenges. So a civil engineer in Mexico City developed a pile system called Control Pile. And you can see a cartoon on the left that shows a pile-founded building, two different pile-founded buildings. The idea of the control pile is that it has an adjustable head frame so that the load of the building is transferred to the concrete pile. These are concrete piles, with a frame that allows adjustment. And so a crew, and this is in the basement, the sub-basement actually, of the Pemex building, one of the Pemex buildings there. And you can see you can see elements inside the sub-basement walls that supported the basement that have this little frame, and the load was transferred. Unfortunately, this confined space was not treated exactly the way it needed to be, and an explosion, or actually a conflagration, occurred because somebody struck a match to light a cigarette, and that the reason I'm able to get the photo that I was because of that damage to the building, which is very sad. And in fact, it had some fatalities. But the idea that a crew had a continuous task to adjust these piles to keep the ground level of the building at the ground surface. So the control pile then, what I've picked out here is a plan for long-term monitoring and maintenance that's built in to allow the structure to exist in the geologic setting that we have to deal with, or they had to deal with at that location. And we'll go to some, wait a second here. Okay, so we'll look at some, we'll change gears, sorry for this, and look at a few other smaller projects that have some complexities to them. There's George Washington Parkway in the Washington, D.C. area. This is actually in Virginia. It's a project to mitigate rockfall. As you can see in the lower photograph here, some rock material has fallen onto the shoulder of the George Washington Parkway, while preserving the natural appearance of the slope. And so what that meant was that rock bolts, the face plates and shotcrete were not allowed to be used because of the impact they would have on the visual appearance. The slope could not be laid back, and I'm not sure if that was entirely to preserve the appearance or in part because of right-of-way, which is certainly a potential problem. So Schnabel Engineering was the lead engineer on this, and they proposed and tested and were able to successfully use polyurethane grout with drain holes because that's impervious. But the polyurethane was essentially a cement that glued the rock blocks together. They had to have the drain holes so that they wouldn't have hydrostatic pressure behind it. So that was a very useful approach. It was, in fact, unique, the first attempt to make that happen. And the one I've picked here is address conflicting regulations and policies. That was the policy to maintain the visual appearance while stabilizing something that was a safety hazard. The next one here is a fault investigation at a school site in Los Angeles. The project was to locate the traces. The school site had been in existence for many years before the fault hazard was recognized. A dense urban setting, lots of buried utilities. Trench exposures is the preferred way of evaluating these fault traces. But in the dense urban area, that's not possible in many cases, and so we were using closely spaced hollow stem auger borings and some geophysics. And the hollow stem augers use no water for mixing mud. It's not needed for that technology. It generates no liquid waste other than the groundwater after that's been encountered. And it has a large diameter barrel, which gives us a good view of the geology in the subsurface. So here you see a diagram where the groundwater was detected, and faults in many settings generate or create groundwater barriers, and that's a clue as to where they are, and we use that along with the stratigraphy, which you can see here, and identified where the fault traces were relative to the buildings on the site. And there's some geophysics. In view of time, we used seismic refraction from the ground surface and then supplemented it with boreholes. We also had a trench where that was possible. So down here, for this one, we'll pick avoid adverse geology, and of course we weren't avoiding it, but we were recognizing it and factoring it into the civil engineering project. Lower Mount Wilson Road is a private road. It was originally built in the 1800s to provide access to some timber resources at what turns out to be the head of a very large landslide. A resort hotel was built there in the 1800s. It burned down as, pardon me, as many of the historic buildings of that era were prone to do. It was taken over by the county of Los Angeles, and the area up there was very well suited to be a lookout location for fire hazard management. So the road was used by hikers, but the only vehicles that went on that road were LA County vehicles. So they're very low. An average daily traffic was like 4 vehicles. It was maintained by the fire crews with their own equipment. A major storm occurred in 2005 that was something that created a couple of locations where the fire department crews were not able to just do their normal maintenance to keep the road open for basically as a single lane road, unsurfaced road. I have a note here that fiber optics line running, this road goes all the way up to Mount Wilson, which is hugely important for communication. A fiber optics line from the community of Pasadena, that part of the urban development up to Mount Wilson, or maybe down from Mount Wilson, was located in this road. It did not break, so that was a clue that this landslide occurred above the road and buried the road rather than displacing the road bed and breaking the fiber optics line. So we decided to do a fix of the road, restore vehicle traffic, vehicle passage, and we did that with a combination of gabion baskets, which you see here in the same site, same location, with a welded wire steep and slope system above it. And on the major landslide right here, we had a welded wire wall with some gabion baskets above that wall to hold the toe from raveling, really. And some very interesting things about this that would take a long time to describe, but this was an innovation of using baskets between a natural rock outcrop and a huge boulder that was part of the slide, probably there before the road was established originally. But this was a county project, and if this had been a public works project, we would have had to have factors of safety and those sorts of things that I rationalized and proposed that we disregard the stability, because this was a private road, one lane, unsurfaced, used only by the fire department for vehicles, and that reestablishing road access would be easy to do or possible to do. It wasn't exactly easy, but it was straightforward. But if we needed to do an investigation for a stability analysis to try to demonstrate something to get a permit that a normal highway would have, that this road would have been abandoned because the cost of the investigation, let alone how the stability might have been able to be done, it probably was not possible. So this is conflicting regulations again. We mentioned that one before, to address those conflicting regulations, and many other things too. There's a paper in the ICE, the British Engineering Sustainability Journal, about this. In Western Australia, the town of Perth has a building that was originally constructed in 2005, 2 stories on a mat foundation, and there was a hole that was for a future building that had just been left in that shape. New owners bought the 2005 building, and in 2008 wanted to raise the height of, create a tower, and it needed to have deep foundations. Now, this has won several awards. It's called the Condor Tower. If you're interested in trying to take a look at that online, you should be able to find this information, which is where I got this. So here's on the left, you see the original Oakley building, mat foundation, 8 stories, and then the 2008 Condor Tower is on the left, where where the tower part needed to have pile foundations. Well, those piles were installed through the frame of the existing building. They did no demo. Well, they demoed walls, but they did not demo the structure. So that was really quite interesting, and that's certainly the leadership and commitment to be able to do that. There's lots of engineering to make that happen, but the idea that it could happen, I thought, was really excellent for the geotechnical sustainability. And then I've got a series of slides here. This is Cape Hatteras Lighthouse was actually moved about 2,900 feet because of erosion that was related in part to sea level rise, no doubt about it, but also wearing away of the beach, maybe even without the appreciable sea level rise just because of large storms. So this was a project from the late 1990s, 1998, 1999, from planning to construction. There's a couple of photos here from Google. The left and right are 1993 and 2014, and then the little insets, the red boxes, are the locations of the insets, and you can see where the lighthouse was by the shadow that it casts, easier than you can see the tower itself, although the black and white striped tower is visible in the photo on the right. Well, this slide renders. So there's a photo of the tower in its original location. It's a granite block foundation and a brick structure, unreinforced masonry structure. What was done to move it was had a geotechnical component. It had a non-geotechnical component also in terms of the jacks and to keep it level, and rollers to allow it to be pushed hydraulically, in a stepwise, very much like some ancient Roman type constructions. And also had the lower part was a steel mat and evaluation of the foundation conditions in beach sand and near shore deposits. So down below, you see what that looks like. Here's the steel mat with the guides. It went about 2,900 feet, 889 meters. A series of investigation holes were done in part by Law Engineering, that became MacTech, and then subsequently A.M.ASCE, and now a wood company. Soil borings were also made by the Army Corps of Engineers. They were overseeing this. So this was quite an undertaking, very high risk, high profile. Here's a pendulum with a circular target, because the tilting of this rigid, brittle structure was really critical. And while it happened, a hurricane occurred. Hurricane Dennis moved across the site, and that's the yellow track there, with the black track with the yellow highlight is the hurricane path. And from 1999, there were a number of hurricanes. That one happened during construction, where the red vertical line is. So this has a number of really interesting things, but again, I picked the leadership and commitment one to highlight here. And now the use of underground space. This is in Lalibela, Ethiopia. It's up on the approximately in the area of A.M.ASCE. I visited this area for a water supply project, but not Lalibela. That was a tourist attraction that I visited. But King Lalibela wanted to create some churches that would serve as a monastery for well, I'll just leave it at that. I won't go into more of the history, although it's kind of rich. But this was done in the 12th century. The problem or the condition here was that durable stones and timber for typical construction were not available here. And so the geologic environment included a volcanic conglomerate, it's called agglomerate, that was soft enough to be excavated with hand tools, but strong enough to stand vertically. So a series of churches, this is the Church of St. George, which is cruciform in pattern in plan view, and one of the most iconic of the 11 churches that are here. It's 3 stories high, and the rooms were created by hollowing out the earth material, the rock, to create those rooms. It's really fascinating and very impressive. So here, what did I pick? Conflicting regulations and policies. I don't know why I picked that one. So I will just skip that. Probably in the wrong place. Extend the useful life, because it's been in operation for, well, since the 12th century. And finally here, the idea that purple is the new green is the reason, or the reason for that is that recycled water, at least here in Southern California, is designated to be in purple colored pipes and facilities. And so here the upper of these 2 photos shows a fire hydrant that we're used to seeing painted yellow. That's potable water. And it's insane that we would use potable water for some of the uses that we're using when the reclaimed water, which is just purified, it probably meets drinking water standards, but because it's been used once and coming from that kind of a process, we want to keep it separate from the potable water that comes directly from the ground. So the point here is that this is suitable water to use for drilling fluid makeup for sure, lab testing perhaps if we're going to use if we want to use water for concrete mix, if that's going to be suitable, or soil conditioning for compaction, or dust control. So I would encourage us all to ask for hookups with recycled water on our projects. If they're available, that's wonderful. If they're not available, just simply asking for it will raise the profile of awareness on the people that need to know about that, or we would like to know about that. And that's a leadership. There's many other things, but lots of leadership opportunities here. So I think I've used up the allotted time, and let me go to Q&A and see if there's anything in there. One of the topics that is real common, and I mentioned this in the first example, the bridge in Oregon, is that much of what is called sustainability, certainly in geotechnical, is what we would consider to be just good engineering, balancing cut and fills and that sort of thing. So what's wrong with just calling things good engineering and having sustainability be part of it? And that's a good concept, and it ought to be happening. But I think the issue that we ought to consider is that we have a word, sustainability, that means so many different things to different people that it would be really helpful for it to be connected to us. And civil engineers, is most of the, if not all of the people on this webinar, will recognize is a triple bottom line philosophy of the economy, the environment, and society. So the public perception of sustainability seems to be dominantly on issues related to the environment. And civil engineering certainly touches the environment in visible ways, notably bulldozer and massive earth-moving projects that have led to a negative view of civil engineering in general, which is unfortunate. But we do a huge number of things that blend in so well that the public doesn't notice them at all. The tunnels for a transit project, I'm working on one of those right now. So I'd say this kind of a presentation is aimed at putting a banner of sustainability on our good engineering practices. So I'm looking here for questions, and I see 0 questions, so I guess either I stunned you or it was perfectly clear. And I think I'm pretty much out of time. So Bhaskar, back to you.
All right. Thank you, Jeff, for these great examples on how sustainability, how geotechnical engineers can actually contribute to sustainability in different ways. And with that, I will move on to the next speaker for the session, which is Dr. Ranjiv Gupta. Dr. Gupta has over 10 years of academic and professional experience in the field of geotechnical and geoenvironmental and geosynthetics engineering. He currently works as a senior tailings engineer for Freeport-McMoRan, a copper mining company based in Phoenix, Arizona. Prior to joining Freeport, Dr. Gupta was a geoenvironmental consultant with Geosyntec Consultants. He received his doctorate from University of Texas, Austin, and has been involved with A.M.ASCE Geo-Institute since 2004. He is going to talk about the heat exchange at landfills, a case study that he worked on. And without any further ado, I leave the floor to Dr. Gupta.
Hey, thanks, Bhaskar. Thanks for the introduction. Thank you, everybody. As Bhaskar said, I'm Ranjiv Gupta. I'm a tailings engineer with Freeport. Today I'm at a site, so you may hear a little bit of the background. So you'll see some equipment or some noise. Apologize for that in advance. And if you want something to be repeated, please just add it to the Q&A session. We can talk to that. So today I'll be talking about heat exchange at landfills, which is basically a case study of an instrumented landfill in Southern California. My co-presenters, Leticia and John McCartney from University of California, San Diego. It is actually Leticia's Ph.D. work. She's defending a dissertation this week, so she's not able to present it today. Then for my colleagues from Geosyntec, Keaton and Jeremy Morris, who I actually started this work with some 5 years ago before I transitioned into Freeport, and with collaboration from Republic Services, which is a waste management company. So this is kind of a work where we have a university industry consulting partnership, and as Jeff gave you examples of some of the, for lack of a better word, conventional geotech areas where we have applied concepts of sustainability or smart engineering. I'll take you into the domain of geo-environmental engineering, where we have kind of taken the same ideas and tried to implement it in that field. So on a very high level, what I'm going to talk about, the big idea for this project is we understand that municipal solid waste landfills, they have like high internal temperatures due to biodegradations, and that can sustain for 20 to 30 years. I think that's been known to us. So what we wanted to do with this project was to understand when we are constructing any new landfill, is there a way to take advantage of that heat which is being generated by the waste and be able to extract it in some manner and then use it to heat up the close by buildings, like your small buildings or what kind of heat is generated and how we can extract it. That was kind of the idea we wanted to work on. We did a case, like a desktop study, and based on the numbers, we thought that the payback period, if we installed some pipes in the landfill as it was being constructed, would be like 5 to 6 years. With that idea, we went to the public services, convinced them that let's try an instrumental landfill, a small portion of a new cell they were constructing, and see how it works. So that's what I'm going to talk about today. Just to give you a background on the site, it's called Sycamore Landfill. It's in San Diego, California. It's owned by Republic Services. So the landfill, where you see the Republic Services is logo, that's where the landfill is. It's about 16 miles from University of California, San Diego, and about 20 miles from the Geo-Institute regional office in that area. So provided a kind of a close opportunity for us to go back and forth and monitor the landfill on a regular basis. And one of the reasons we wanted to do it in California was in San Diego, which worked out was like the annual temperature is roughly 65 degrees Fahrenheit. It doesn't change that much, so at least we had that kind of as a baseline. It rains roughly like 12 inches in a year in San Diego. So 3 main objectives from this work. Definitely understand some of the in situ thermal properties. There's been a lot of literature which has been published, so we just wanted to verify if we were going to get same data, and then kind of understand what is the potential for heat extraction at a municipal landfill, and then also start putting some kind of a framework together to understand if we could, based on the heat extraction potential, if we could predict what kind of heat you can get and for how much duration. And I'll go into the details of the experiment we did. So in terms of field installation, this is kind of the overview of the landfill cell. It's about an acre in size. If you were to, I know I don't have a pointer here, but it's roughly an acre cell. So what we did was instrument roughly 100 feet by 100 feet area at the very edge of the landfill, where you see geothermal heat exchange pipes. So that's where we installed those pipes. And then on the edge of the landfill boundary, we had a generator, a chiller, and a data acquisition system. So, and I'll explain how, in the coming slides how we use those to kind of calibrate our model. Just a quick summary of what the landfill liner system looked like. So our heat exchange pipes were sitting on top of a protective cover, which is generally a select waste. It's about 2 feet thick, which sits on top of a 12-feet drainage layer. And then the liner system consisted of a geomembrane, a geosynthetic clay liner, and another geomembrane at the very bottom. In terms of our geothermal system we put in the landfill, it's pretty much a standard HDPE pipe. We had 2 loops going on. It was a 1-inch thick pipe, and we covered an area of roughly 100 feet by 40 feet, which you see on the picture on the left. So you have a pipe going in a kind of a loop configuration. And then on the right, you see 4 strings, which is primarily the temperature sensors, which we installed along the edges of the pipe, so we could understand how the temperature varies along the pipe cross section. And before we covered the pipes with the waste, we ended up filling it with water just to make sure the pipes are not going to get compressed. In terms of so once you install your pipes at a given layer, we discovered it with some protective cover soil, install a thermistor strings, which are the temperature sensors, and then came up and pushed waste on top of these geothermal pipes. And the picture on the right kind of shows the 3 layers we installed these geothermal pipes on. So there's a layer 1, which is sitting right at the bottom of the cover system, and then you have another layer 2, which is 20 feet up, and then layer 3, which is another 20 feet up. This landfill totally itself was like 100 feet high, so you have another 50 plus feet of waste on top of layer 3. And then once the pipes kind of daylighted on the edge, we put some fiberglass on it so we could insulate those pipes as well. I know the picture is very small, but you can see there's a data acquisition system, DAQ, where all the temperature sensors kind of reported, so we could kind of collect temperature data continuously. And then towards the end, we have a water chilling and a generator system, and I'll explain what we did with those. So that's just giving you a kind of a close-up look of the same. So you have a layer 1 of geothermal pipes sitting right at the bottom of the liner system. Layer 2, 20 feet high, and then layer 3, 40 feet high. And then you see the black wires, which are your geothermal pipes coming out of the landfill. Just an instrumentation layout in terms of cross-section. Again, the same picture, but you see another 120 feet of pipe. We have 4 sensors. The blue is closest to the edge. Then you have green, yellow, and then a dark green shade. So roughly 12 sensors and 4 per layer. Just at each layer, looking from the top, we also installed the blue lines A, B, C, and D basically show 4 arrays of pipes. So we wanted to also see how the temperature varied laterally within a given layer. Then we also have 2 red dots, which are our water temperature sensors. So the idea was you would be circulating water, running it through a chiller. So basically the C here, which will send it to like 50 degrees Fahrenheit, push it through the loop. So once it goes through the loop and comes out on the other end, you'll see how the water temperature changes once it's made its way through the pipe. So we divided this project into 2 stages. So the first stage was just to understand how long does it take for a temperature to stabilize within the landfill. So we put these pipes and temperature sensors in and monitored temperature within the landfill for a year. And roughly at 13 months is when we saw the temperature stabilized, and we didn't see any more further increase in temperature within the landfill. And then in the second stage, once the temperature was stabilized and we understood, okay, there's no more change, we implemented our heat extraction system, wherein we pushed cold water at one side of the loop and measured it coming out on the other side. We ran this experiment for 17 days, and our target temperature was 12 degrees centigrade or 50 degrees Fahrenheit plus or minus. So in stage 1, this is when we started our experiment in August. We measured the temperature within the landfill. At this stage, we just have temperature sensors which are measuring our ambient temperature, which is the one in gray, and then the 4 sensors on layer 1. The blue being the closest to the edge and most susceptible to the ambient. But you can pretty much see once you get 50 feet roughly within the landfill, the temperature kind of stabilizes and doesn't have that impact from the ambient. And then it kind of becomes steady. And over a year, we saw roughly 90 degrees Fahrenheit at the max. There's a data gap where our batteries went away, but I think once we replace them, we can see kind of it picks up towards the end in the same trend. So this just gives you a progression over time for all the 3 layers. So what you have on your y-axis on the left is the elevation, so 0, 20, and 40 feet. That is layer 1, layer 2, and layer 3. Then the bottom, I'm showing you the temperature. So the idea is the bottom, the layer, the one at the elevation 0 feet is roughly at the, pretty much remains at 30 degrees C and or 90 degrees Fahrenheit. And then as you go in towards the middle layer and the third layer, over time the temperature has increased but layer 2 and layer 3 kind of are roughly at 50 degrees Celsius or 120 degrees Fahrenheit, the end of the year. If you were to just take a photograph of a given snapshot, this basically just shows you at one given time how that heat contour would look like. So we, based on this, if you look at the slope face and then look inside, like there is a zone where you can kind of see there's a constant stable temperature within the landfill cell. So in the second phase, once we established that there was a stable temperature within the landfill, what we did was so just to explain you this graph, on the left we have temperature, then on the right side we have the volumetric flow of water. So the gray line corresponds to the volumetric flow on the right, which is we try to push constant amount of water within the layer 2. And on the bottom we have time in hours, which is 450 corresponds to roughly 17 days. So the blue line shows the water going in at 20 degrees Celsius, and then the water which is coming out in the orange line up is 35 degrees Celsius, plus or minus. And based on that, Leticia in her dissertation has talked about the line analysis, heat analysis, and has come up with the waste character, like the thermal properties of the waste, about 1.3 watts per meter centigrade. That gave us some confidence that, okay, there is a way you can extract heat and then at a continuous basis within the landfill. So in summary, we were at the very stage of this project, we were able to install a geothermal heat exchanger system within a municipal solid waste landfill. We roughly saw 45 degrees Celsius in less than a year, which showed us there was a potential to extract heat. And based on this preliminary data analysis, we see that the average in situ thermal conductivity of this is roughly at 1 watt per meter centigrade. This project was sponsored by CAPES, which is a scholarship from Brazil, which Leticia got for research, Geosynthetic Consultants, which are the geo-environmental consulting team, which put this project together, and Republic Services, which are the waste producers which gave us the site for this work. With that, that's my last slide. I'll switch over to Q&A. So I think the only question I see is what is roughly the cost of this project? So we ended up spending roughly $15,000 on the HDPE pipes. We rented the chiller and the dead acquisition system for $7,000, so we've roughly spent less than $25,000 till date on this work. And yeah, it does show some potential, like we can extract heat from the landfill. It's been a very promising project till now. I don't see any more questions, so I'll transfer it back to you, Bhaskar.
Hi, Ranjiv. Thank you for this good presentation, and it's really a great idea. I have one quick question though. So, what are the next steps for this line of research? Like, should other landfills start looking at this sort of heat acquisition?
I think there is definitely a potential. Yes. So a very good question. So we did it in California. I think since the heat, depending on the size of your landfill, the heat potential may be minimal to quite big. So you have to kind of think it through. And to be cost effective, it has to be done in the beginning, like before you start putting waste. I think if you start drilling to put these pipes in, I think that it will become cost prohibitive very quickly. And if you have a small, let's say a landfill office or something, it's much easier to use the heat from this source. I think that is where I think I would not take it too far based on this work. Right? I think there is potential if you have a small landfill, like an office building, you can use this heat on some basis to do that right now. So that is where we are with this research. And I think Leticia, if she was here, probably could talk a little bit more. I think we're getting more into analysis now with the data to understand how far can we extrapolate these results.
Great. Excellent work. So if there are no other questions, I think we can move on to the next presentation. So the next presenter in this line is Das, Dr. Jasaswee Das. He's the, just give me a quick minute. Yeah, he's a geotechnical engineer with Intertech PSI in Dallas, Texas. He completed his Ph.D. from the University of Texas at Arlington and M.ASCE from the University of Texas at Austin, both in civil engineering. At UT Arlington, he served as the president of the A.S.CE Geo-Institute chapter. He serves as a young member on the AFP 40 Standing Committee on Transportation Research Board and is an associate member of the A.S.CE. He has authored and co-authored several journal articles and has patent pending with USPTO. So without any further ado, I leave the floor to Jasaswee.
Thank you, Dr. Chittoori, for that introduction. Good morning to all of you who have joined this webinar. The next presentation is going to be on sustainability and resilience in pavement infrastructure, specifically how we can integrate the concepts of sustainability and resilience into a meaningful unified assessment. Over the next few slides, I'm going to walk you through a framework that we conceived at the University of Texas at Arlington. It is a quantitative framework that combines the metrics of sustainability and resilience, which we'll also discuss. And I'm also going to demonstrate to you the applicability of this framework through a case study. So it's not just a theoretical framework, and I'll try to convince you of this framework's utility in the practical world. Now, due to time constraints, I may not be able to discuss this framework more elaborately, but I'll guide you to the full paper which we recently published based on this framework. So let's dive in. Regarding the structure of the presentation, I'll start with a brief background on sustainability and resilience with respect to transportation infrastructure, then go through some of the past studies that have been undertaken in this area. I'll then introduce the framework, give you an overview of the case study, the field implementation project, and then we'll conclude. And by the way, I must warn you that some of the fonts and figures may be a bit off. It's just because of this online interface and not the way the slides are originally created. So please bear with me. Let me start by showing you the 2017 A.S.CE infrastructure report card to emphasize why we need sustainable and resilient infrastructure. So this is the poor state of transportation infrastructure in the U.S. And if you see the road sector, they were ranked at a subpar D grade. As you know, pavement infrastructure are an important component of the built environment. They connect supply chains, enable trades and businesses, provide access to healthcare and education. And there are several challenges such as industrialization, aging, natural hazards, etc., affecting the pavement industry. These are some statistics concerning transportation infrastructure, and it shows the percentage GDP that different countries spend on transportation infrastructure. In the US, it is about 2.4%, and that translates to an underinvestment of $800 billion. Now, one of the earliest definitions of sustainability was given by the Brundtland Commission. What this definition essentially means is development that is sustainable in the long run. And by the way, we can use the terms sustainability and sustainable development interchangeably. Sustainability is maintaining equilibrium among the environment, economy, and society. Or in other words, sustainability sorry, there's an issue with one of the animations. In September, I believe 2015 was the year, the member nations of the United Nations adopted these 17 Sustainable Development Goals, which should be achieved by each nation by the year 2030. And please note Goal 11, which focuses on sustainable and resilient infrastructure. Now, researchers suggest that the scope of sustainability is highest at the beginning or planning stages and decreases drastically as the project moves toward the implementation stage. Therefore, it is necessary to incorporate principles or best practices concerning sustainability and resilience at the initial stages or at the conception of a project. Now let's talk a bit about resilience. The conceptual definition states resilience is the ability of communities to withstand shocks or perturbations to their infrastructure and to recover from those effects. Analytically explaining, if we have a function Q as a function of time, which denotes the quality of an infrastructure or the robustness of construction. And let's say at time T is equal to P sub D, a natural calamity or a natural hazard strikes and the infrastructure loses its full functionality, goes below 100%. And at time T is equal to P sub R, the system recovers its functionality, although not completely. Then the loss in resilience is mathematically represented as that equation that you see on the bottom right of the screen, which is basically the area under the curve. Resilience is characterized by these 4 properties, and I apologize for the figure, the font is a bit skewed. Anyway, so the 4 properties are robustness, or the capacity to withstand a certain level of stress without functional damage, redundancy, or the extent to which an infrastructure component is substitutable in the event of damage, resourcefulness, or the ability to identify disruptions and set up mechanisms to address the same, and rapidity with which the external disturbances are addressed and the losses are contained. So to summarize, a combined consideration of resilience and sustainability is indicative of the quality of an infrastructure. The next few slides list out some past studies on sustainability in pavement infrastructure. we're not going to go through them in detail due to time constraints, so let me skip a couple of slides. Now, most of the past studies highlight sustainability, but they do not adopt a combined or a unified approach linking sustainability with resilience, and that is something that we tried to attempt through this framework. There were three major objectives. One, the identification of metrics for sustainability and resilience. Two, development of quantitative framework. And three, defining the quality of infrastructure, taking into account both two aspects of sustainability and resilience. Now, please note that the framework that I'm about to introduce does not provide an absolute value for sustainability or resilience. It merely facilitates comparison or assessment of the relative sustainability and resilience of the different competing alternatives. So when I say alternatives, as in, let's say, whether for a particular project, whether you want to use piles or drill shafts, or let's say a segmental MSE wall or a Gabion wall versus a gravity wall or a CIP wall. So when you have like a bunch of alternatives, we can use this framework to gauge or assess the sustainability and resilience of these different competing alternatives to come up with a suitable choice. Now, let's dive into the framework conception. This flowchart explains the framework a bit clearly. This approach is simple. It involves normalization and weighting, weighting as in attaching weights to the different impact categories based on their relative importance. We'll have an extensive discussion on the weights later on. So we have our alternatives. Unfortunately, I do not have a pointer with me. So we have our alternatives. Next, we identify the individual impact categories through life cycle assessment and life cycle cost analysis. The impact categories are listed in the International Organization for Standardization Standards ISO 14047, and the LCA is in accordance with ISO 14000. The LCA estimates the environmental impact and the embodied energy. So you can see two parts. One is the life cycle inventory analysis and the environmental impact assessment analysis. You can also see the different impact categories under each assessment. The LCCA gauges the socioeconomic impact. And coming to the resilience part, based on the properties that we discussed earlier, we identify suitable representative impact categories for resilience. For example, in this case study, we used the reliability index and the probability of failure, which we'll discuss later. Now, all these impact categories are internally normalized according to weights based on their relative importance, and we finally designate the sustainability index and the resilience index. The ultimate step involves multi-criteria evaluation of the individual weighted indices to determine something called the quality index or IQ. Now, the quality index represents the combined degree of relative sustainability and resilience, and the alternative with the least index is considered to be most appropriate. I mean, it might sound a bit counterintuitive, but that's how the framework has been conceived. So bear in mind the index with the least value will be considered the most appropriate among the different competing alternatives. So these are just the different metrics we talked about earlier. The life cycle inventory is performed based on the embodied energy. And let me just show you one of these. It's difficult to, for time constraints, it's difficult to go through all these tables, but let me just show you one quick table how we come up with a calculation. Let's say we have for the environmental impact assessment, we have the first column, the environmental impact categories, we have global warming, acidification, eutrophication. So for the different alternatives, we have our values in the subsequent columns, column 1, column 2, and so on. Then you see the percentage contribution, which is basically a sort of normalization, which we perform on the values in the preceding columns. Then we attach the weights. And finally, we have our weighted impacts to give the environmental impact index, which is basically the summation of all the weighted impacts. So that's how the framework is developed. And the final aim or the final goal of the framework is to enable a visualization or a graphical tool. So let me skip to so at the end we'll have something which looks like this. This is a radar chart representation. All these results, as you can see, have been internally normalized. And the beauty of this approach is that you can have any number of metrics for comparison purposes. In this polygon, we'll just add more nodes the more the metrics you have. We can also have a bar chart representation. We can graphically plot those results on a bar diagram which show different weightages. The bar chart provides a nice tool to the user to make informed decisions and to select alternatives based on a trade-off between sustainability and resilience. For example, if the engineer wants, let's say, 10% sustainability and 90% resilience, then he can choose alternative 1, which is basically S sub 10. I wish I had a pointer, which is basically S sub 10 and R sub 90. So those basically represent the weightages attached to both these aspects. Let's say we have, let's say we wish 70% sustainability and 30% resilience, then we'll end up with alternative 2, as you can see. Now bear in mind the alternative with the least index is considered better. So as you can see for S70 R30, alternative 2, the one in orange, that has a lower quality index, and that is considered to be better from a combined sustainability and resilience point of view. Now, the most important thing about this framework is the weights, because the weights can be pretty subjective. So it's essential to come up with an approach to streamline these weights. Now, for this framework, we have a flexibility to the engineer to attach weights, and in order to prevent any bias, the impact categories have been assigned equal weightage, but of course the weights can be, I mean, we could have a consensus on the allocation of weights. In fact, we tried to have a broad consensus by performing a survey. This was one of the questionnaires that we handed to some attendees at the A.M.ASCE conference in Florida last year. So based on the survey statistics, we came up with like what sort of weights would be more comfortable and something which the industry professionals are comfortable with using. Let me talk about the case study a bit. So this is subgrade stabilization project that we had. This is a research study supported by the Texas Department of Transportation, TxDOT, in Fannin County, Texas. So at the bottom right inset, you can see the test section. The annual average daily traffic on this highway was around 8,000, so this could be classified as a high volume road. The soils at the site are expansive clays that possess a high sulfate content. So sulfate-induced heave was an issue, and we tried several combinations of lime and fly ash to stabilize the subgrade soils, and based on the lab studies, we decided to use 6% lime. And then we also decided let's add some fly ash to limit the available calcium for actinide formation so that we do not have sulfate-induced heave. So we came up with two test sections. Section 1 had 6% lime and 3% fly ash. Section 2 had 6% lime. This is the construction details. Both these sections included 7 days of mellowing, and both these sections are also monitored continuously for a period of 2 years. This is just the framework which we discussed earlier. We have our alternatives, and we finally come up with the quality index. These are some of the assumptions for this case study. We had the section dimensions. We calculated the mass of the soil that was to be treated, the mass of the material. We assumed the mileage of the dump truck and the capacity, the average distance. So we need these data in order to perform the assessment. The next few tables are just assessment framework. I already showed these. Let me just finally show you the result. For sustainability, I think I just touched upon it a bit earlier. For sustainability, we used the probability of fatigue cracking and probability of rutting failure, and we also combined them with the field readings. We had the readings for the modulus which we had from polymer deflectometer test, and we also recorded the present serviceability indices. So based on that, we found our resilience index, and we combined everything into this radar chart. And as you can see, just on the radar chart, test section 2 has a test section 2 has a low IQ value based on the radar chart. So that is considered to be a better alternative. In conclusion, as I mentioned, the framework facilitates a unified assessment of sustainability and resilience. It provides powerful decision-making tools to engineers and other stakeholders for selection of appropriate alternatives. It allows some flexibility in assigning weights to the impact categories and metrics. And finally, and more importantly, we have a pictographic representation of all the elements. So it enables comparison among any number of competing alternatives, among any number of metrics. So that's it, and this is the full paper. For lack of time, I had to skip through the presentation quickly, but this is the full paper, and you can go through this. If you have any questions, feel free to drop me an email. Thank you. If you have any questions, please let me know.
Let's see if there are any questions on the QA.
I don't see any questions in the Q&A. Okay, so I guess over to Dr. Chittoori. Thank you.
Thank you, Dr. Das. This is a very interesting framework, and I think there is a lot of additional work that's needed on this. What do you think about the, like, what should be the future for this? Like, what are the next steps in making sure, like, somebody uses this sort of framework?
So, in my opinion, I mean, the weights, the defined analytical categories, the terminologies, etc. I mean, they all could be debated and improved over time with discourse, especially the weights. I mean, we could have a better consensus over weights because the choice of weights might skew the analysis. So once we have a consensus over weights, this framework could have a better implementation and usage in the practical world. So definitely all these weights and categories could be improved, as I said, with discourse, but I feel the conceptual framework is significant.
Yes. Yeah, and I feel the weights are also very important. Like, how do we decide, like 90% should be weighted towards resiliency and 10% towards sustainability, or the other way around?
I think that's why. So that's the reason why I showed that bar chart with all the different percentages. So I do not want to, like, it will vary depending on the project, the nature of the project. I mean, for a critical project, resilience may be more of a concern compared to sustainability. So the engineer for that specific project might use a value which is skewed more towards resiliency side than sustainability. Similarly, for a project, let's say in an environmentally sensitive area, the engineer may opt for more sustainability aspect compared to resiliency, and so that's why I just provided the entire spectrum, the different combinations of sustainability and resilience weightages. So it's up to the user, but of course, as I said, a broad consensus needs to be evolved, and that can only be accomplished by discussions with different stakeholders and industry professionals and federal agencies, state agencies, and everyone. So, so this framework just shows the way forward. I mean, it's still, I won't say it's a sophisticated or finished product. It's still in development, I would say.
Yep, and very good step towards, unification of sustainability and resilience. So thank you for your presentation. You actually took less time than I expected, which is good.
Yeah.
Probably leaves more time.
Yeah, I was trying to skip through some of the slides. I didn't want to. I wish I was the last presenter, then that way I know how much time I have left, but I didn't want to take much of your time, so.
Thank you. So with that, we will move on to the next presenter, which is myself. I am a faculty member at Boise State University, and I do quite a bit of research in expansive soil and ground improvement, but all of them, one way or the other, rotate around sustainability and resiliency. So in today's presentation, what I am going to talk about is a good, I think, good lead-in from what the earlier speaker, Dr. Das, has mentioned, which is unification of sustainability and resiliency. We are doing a similar thing by accounting for risk as well, but for earthen dams. So that's what I will be talking about in this presentation. So let me quickly pull up my presentation. So, so like I said, this is a unified approach to sustainability, resiliency, and risk assessment. So this is a work in progress. We did come up with a framework, and there is an example that we are showing how to use the framework. But there are still lots of variables that need to be accounted for, and there is, like Dr. Das was mentioning, the stakeholders of operating these infrastructures, either building them or operating them, are key players in ensuring that these frameworks are more practical and usable for them. So this is essentially a first step in that direction. So this is a brief overview of my presentation. I'll start off with some introduction. Overview of sustainability and resilience. I don't want to re-emphasize what Dr. Das already mentioned, so I'll glance over them quickly. And I will present our framework and what we have, what we are proposing, and how the proposed framework can be used, and then indicate some future research steps, and towards the end I'll summarize the framework. So with that, introduction. So the sustainability and resiliency being considered as two separate entities and having frameworks to assess both of them separately has been challenged by few earlier researchers, especially because there are a lot of similarities in which in the way they are assessed. Both require some analysis of life cycle assessments to study the impacts. And both analysis study the impact of all the three triple bottom lines, the economy, environment, and societal aspects. So with that in mind, what we try to come up with is a framework that would be useful for not only from the engineering point of view, but the decision makers point of view, where the framework should be able to unify both the sustainability and resiliency aspects, but also there is a great value in assessing both of them together because of how the climate is affecting the infrastructure. There are lots of high-intensity floods and other events that are causing the infrastructure to be impacted much more often than it would have been in the past. So now would be a very good time to look at these interplay between sustainability and resiliency and come up with a framework that assesses both of them. At the same, so while accounting for both sustainability and resiliency, it's also important not to forget the risk associated with the hazard, because if the risk is not too high, then being too resilient is not being very sustainable. So there is obviously an interplay between all these things, and how we can give the decision makers a tool to play with these to see which project alternative is going to make most sense from all these three aspects. So that's the goal for this, and this is, like I said, an initial foundational research towards this goal. So sustainability is triple bottom line, people, planet, profit. That's what we all have agreed upon. And then resiliency is primarily defined from these 4 R's, the robustness, resourcefulness, rapidity, and redundancy. So the robustness is basically how strong the infrastructure is to a hazard. So if the structure is very robust and there is no impact due to the hazard, then the resourcefulness and rapidity and redundancy are essentially moot. But the robustness of the infrastructure is functional with a lower sustained functionality. Maybe it's only 50% functional. That's where the resourcefulness, rapidity, and redundancy come into play, where how fast can we bring it back to its normal operation capacity, or maybe take it beyond, depending on what the goal is at that point and what the options we have. So that's the definition of the resiliency. And then the risk is, we are defining the risk as per the Army Corps of Engineers definition, which is risk is a measure of the probability and the severity of undesirable consequences. So risk is not only just the probability of the occurrence, but what is the consequence of that and what is the frequency of the event. So all these three make it a high risk situation or a low risk situation. So we are accounting for all these three when we talk about risk in our analysis. So what should this framework look like? A good framework would measure sustainability and resiliency of its infrastructure based like accounting for risk as well. And then the framework should be adaptive for various types of inputs or parameters that need to be accounted for for that particular infrastructure. Sometimes the analysis has to be very deep in terms of accounting for all and every possible parameter. Sometimes the analysis need to be very superficial because the decision makers are not really very too much into the depth of these assessments. So the framework should be able to accommodate both these depth versus the breadth of these parameters. And then some way to plot this or visualize the sustainability and resiliency indices in such a way that it's easier for the decision makers to see and understand where one alternative is falling compared to the others. And then it has to be, our goal is basically make it simple yet robust so that it is usable by practitioners. If it is too complicated, the practitioners probably will have resistance to using it. But at the same time, if it is too simple and not robust enough that it can predict these sustainability and resiliency index accurately enough, again, nobody's really going to use it. So our goal is to be cognizant of both these aspects of the framework. So this is our outline for the framework. So sustainability is primarily the three triple bottom line: the economy, environment, and the society. Resiliency is the robustness, redundancy, rapidity, and the resourcefulness aspects. And then the risk is the probability of the stress event. That means how probable is the event for it to occur. And the second aspect to that is once the event has occurred, what is the loss of functionality? And how much probable is the loss of functionality? If it is 50% loss is expected, how probable is that aspect as well? So we are trying to account for all these three and then come up with some index values that can be plotted so that we can see how this the infrastructure is faring, whether it is high sustainable, low sustainable, and low resilient, or the other way around, or good in both sustainability and resilience. So the next few slides I'm going to quickly show how the framework steps are going to work, and then I'll follow that up with an example for an earthen dam. So the basic steps for the framework are to first choose the system of analysis, whatever the system is that you would like to analyze, and then do a sustainability analysis with the triple bottom line as the basic. So you account for the economy, environment, and the societal impacts for that infrastructure due to its construction, and so on. And then report that sustainability in terms of dollar per year amount. So because we are looking at it from a life cycle cost analysis point of view. And our idea is to basically account for the each one of these, sustainability, resiliency, not in terms of, but especially when it comes to sustainability, the societal impacts and the economic, environmental impacts, if they are measured in metrics other than the dollar amount, it's sometimes hard to visualize their impact. So what we try to do is try to convert everything in terms of a dollar per year amount so that we can relate to them much quickly than like carbon emissions versus some metric for societal impact. So after doing the sustainability, we'll report the sustainability results as a dollar per year. And then do a probabilistic hazard analysis. That means we can look at what are the different hazards the infrastructure can be subjected to. That can be earthquake, that can be flooding, that can be various scenarios. And for those scenarios, what are the possible outcomes in terms of loss in functionality? And once we know that, loss in functionality, then the 4 R's are basically the 4 pillars of resiliency can be assessed. And then we did a secondary sustainability analysis, because when the infrastructure gets impacted by a hazard and there is reconstruction activity, then there is again material use, there is again construction activities, and these are all causing impacts on the society, environment, and the economic part of this. So that's how we are trying to marry this resiliency aspect with the sustainability as well. And the risk comes in while we are doing the probabilistic hazard analysis for this. And once we are done with both these steps, then we report these values as a scaled index value and then do a graphical representation of this. So let me walk you through these steps in a little more detail. So the first one, sustainability. Sustainability has 3, sorry, I need to click on the wrong animation button. So sustainability will lead to the environmental, economic, and social impacts. And each one of these have their own metrics. So there is emissions, carbon emissions can be measured for the environmental impact. Embodied energy is another metric. Economic, we have both the construction cost and the maintenance cost that needs to be accounted for. This maintenance cost is operations and maintenance cost. And for the societal, we have to look at what is the social burden for this infrastructure, like how is the society being impacted during the construction or due to the construction of this, and what are the advantages for this. For example, if you're building a highway, yes, during construction, there is an impact on the society because there will be much congested roads and so on. But after it is done, there are benefits of using that particular road for ease of access and so on. So these aspects are assessed in the sustainability side of this framework. And all these will be combined into $1 per year amount. And that's what we are assigning as sustainability index. And then for the resiliency, we start with the probabilistic hazard analysis. So what are the possible hazards that this infrastructure can be subjected to? And due to that, first thing that will be assessed is the robustness. How robust is it under that hazard? And once the robustness is assessed, the change in functionality can be assigned based on how robust the system is. And based on that, we can have a robustness index, and then we have to talk about the rehabilitation efforts. And the rehabilitation efforts are the ones that will lead to the resourcefulness, rapidity, redundancy, and the hazard-related sustainability. Resourcefulness is how effective, like how close are the materials that we need. Resourcefulness can be talked about in terms of the materials point of view, in terms of the budget point of view, and various aspects of being resourceful. Rapidity, as the name indicates, is how fast we can get the infrastructure back in place. And redundancy is there any alternative infrastructure to replace this as a short-term alternative or not? And then hazard-related sustainability, what would it take to make this infrastructure back to its full functionality or some portion of its functionality? So all this resourcefulness is material required for rehabilitation costs, Rapidity is the time to rehabilitate additional systems in place that can be used for redundancy. All these will give us a rehabilitate index, and then the hazard-related sustainability has been normalized to the original sustainability numbers that we first did in the first step, and they yield a scaled R value, which results in some of the resiliency aspect of the index. So once we have the sustainability and the resiliency, we can plot it in this Cartesian system, where on the y-axis we have the resiliency and on the x-axis we have sustainability in dollar per year. So if a system falls in the upper right quadrant, the first quadrant, this represents the desired system, which is very high sustainable and high resilient. If it falls under any of these two, second or the fourth quadrant, the ones in yellow, they are quadrants that represent some caution. They are either very good in resilience or very high in sustainability. And then we have the third quadrant, which is the most undesirable of the three, which is not really a desired system at all. So we need to be able to plot our infrastructure in one of these three quadrants, four quadrants. We will be walking through the next few slides are basically to give an example of how this infrastructure could be used. So the system we have chosen is an earthen dam, which is very close to where we are. We are in the sense Boise State, and we collected most of the information about this dam from the Army Corps of Engineers, and because this is a dam controlled by Army Corps of Engineers, not all information is publicly available. So we had to make some assumptions about the internal geometry for this infrastructure. And we also obtained historical data on the economic and societal impacts of the dam to account for how these three triple bottom line of sustainability can be assessed. And I want to insist here that this is an example of how the infrastructure or how this framework can be used. So there are things that we have considered and there are things that we have not considered during this analysis. I will point them out as we go along, but keep this in mind that this is an example for using the framework, a simplified example. So for the sustainability, the environmental impacts, so we use the construction activities as the basis for the environmental impacts. So excavation is a part of it, transportation of the material and compaction of the material. So during the construction, because this is an earthen dam, the process is fairly simple. We bring the material from the predetermined site and bring it on site and then compact. So we used the time to complete the job and the fuel consumed for the energy and the emission computations from the caterpillaring, because we assume those are the equipment that were used during its construction. Obtained the EPA emissions factors for the assumed construction activities from Office of Transportation and Air Quality, US EPA. And then combined the construction activity emissions and the quarry emissions, because that's where the excavation is happening for the material that needs to be brought on site, from the EPA calculator, and used those values for the environmental impacts. For the economic impacts, it's fairly straightforward. We know the materials that are being brought, and we know we assume the cost for the construction from the historical records, and use the average annual maintenance budget as a supply value. And we yearly maintenance fees based on literature from A.M.ASCE, again, US Army Corps of Engineers. And we distributed these costs as an annual worth over the design life of the dam. And again, these are all assumptions that we did to again show how the framework could be used. And we also use the average annual inflation rate from the IRS to account for how the money, because when we are talking about the annual cost and looking at the life cycle cost, we need to have these inflation rates in place to account for the money, time value of the money as accurately as possible. And then for the social impacts, we looked at the land loss due to the filling of reservoir, because whenever there is a dam being built, there is huge land that needs to be purchased, and land is lost from previous owners. And the other societal impact we looked at is the recreational usage of the reservoir and the facilities, because once the dam is built, there is a reservoir, a lot of recreational activities happen at the dam. And also the function of the dam. The dam is basically a flood control dam, so it is preventing damage and from seasonal flooding. So that's a very big benefit from the societal impacts point of view. And on top of that, it is producing hydropower generation is a benefit for the societal impact. And also there is assumed water used for irrigation for farmland, which is actually not really a part of Lucky Peak's dam's function, because it's mainly a flood control dam, not an irrigation dam. But because there is water available, it is used for sometimes used for farming as well. So these are all the aspects that were considered while developing the or assessing the sustainability for this infrastructure. And I'm not showing any of the tables that accompany with these things like Dr. Das did, but I'm just showing the final numbers that we came up with. So the environmental impact turned out to be a negative value, because it is a negative impact on the system. The economic impact, again, because it's a cost that's being incurred, we gave a negative number for that. From the societal impact, there is certainly land that's lost, which is basically bought, but due to the hydropower generation and the if you assign a life cost on the flood control aspect of this dam, it turns out to be a very positive impact on the overall societal impact. So that turned out to be a very, very big positive number. And these are some additional numbers for the fuel burned during construction, the total embodied energy, and also the carbon emissions during the construction of this dam. So this number is basically combined and assigned as a sustainability index value, which I'll show in the later slides. The next step is basically the resiliency aspect of this. So we looked at, for the seismic hazard analysis, we primarily talked about, or were looking only at the earthquake potential for this, although the earthquake's potential in this area are fairly low. Again, like I said, we are just looking at an example, so we thought we will look at the earthquake potential for this. And we used the various peak horizontal accelerations due to different intensity earthquakes, and subjected this earthen dam to earthquake loading. And we used Geo-Studio to model all this, and we came up with some analysis numbers that showed various functional losses for different intensities of these earthquakes. So the way we went about the robustness is we used the probability of the earthquake from USGS. For a magnitude of 5, what would be the probability for that? Magnitude of 6, what is the probability? And as the intensity went up, the probability went down, because, like I said, this is not a very high earthquake prone area. So the total probability of failure from the change of factor of safety and the probability of the hazard. So the way we accounted for the combined effect of all these individual earthquakes that could cause functional loss is by looking at the total probability. So total probability of failure is the summation of the probabilities of A and B, where A is the probability of the hazard and B is the probability of the failure. So if a hazard occurs, what is the probability that it's going to cause failure? Like for example, an intensity of 4 or 3 may not really have any impact on the dam, but an intensity of 6 or higher will certainly increase the probability of failure correspondingly. And we accounted for all these aspects and came up with a total probability of failure value. And that total probability of failure value looks something like this. So if the magnitude of earthquake is 0.5 or 5.5, the probability of occurrence of the earthquake is 0.263, which is very low, or sorry, a relatively higher number. But the probability of failure due to that is pretty much non-existent. So the factor of safety still remained above 1. Then the magnitude of earthquake, if it is 6, the probability of earthquake occurrence is slightly lower, but the relative probability of failure is slightly higher now, and so on and so forth. So we came up with, so we accounted for all this, and we used a total probability failure of 0.054, and we assigned a robustness value of 0.946, which is basically trying to account for the various not only the impact of a very high intensity earthquake, but trying to account for the low intensity and their corresponding probabilities, and we assigned a robustness value of 0.946 for this particular dam. And then once we have assessed the robustness, the resourcefulness aspect is assumed. We assumed that the rehabilitation is to basically get the slope back to 100%. So we targeted 100% rehabilitation functionality of the dam, and assumed the material required for the replacement is same as the critical slip surface of the failure. So this is another assumption we made is, so whatever the Geo-Studio analysis showed in terms of the critical slip surface, we assumed that as long as it's not a critical failure where the rest of the dam can be expected to be pretty much washed away. In those cases, the entire dam reconstruction is considered. But if it is a relatively shallower slip circle, which is only if it is a superficial failure, then replacing that would pretty much bring it back to 100% functionality. And that's how we assessed the resourcefulness. And the way we computed resourcefulness is basically by supply demand over supply, where the supply is the average available repair budget for this particular infrastructure, and the demand is the required cost for these repairs that's needed. So if the budget is very high and the demand is low, then the computed resourcefulness index is quite high. But if it's the other way around, the resourcefulness is quite low. So that would pretty much assign a number for the resourcefulness aspect for this infrastructure. So the way the resourcefulness, so these are some numbers that are trying to show how the resourcefulness numbers are changing based on the magnitude of this earthquake. And like as the earthquake, obviously, like the more it goes towards 7, that means the entire dam is under distress, so the cost to repair is quite high for that particular intensity. And then based on the impact and the available cost for the repair budget, and the way we came up with this resource budget is we looked at the documents for who owns the dam and how much resource allocation is there for maintenance for this particular for this infrastructure. And again, that's an assumption that we made, which is still coming from the Army Corps of Engineers, but again, it's not accurate. But again, if we had that accurate number, we can directly use it, and this is how those numbers turned out to be. So as you can see, if the earthquake intensity is quite high, the resourcefulness index is going into the negative. So again, we used the same total probability application and then came up with this resourcefulness number to be 0.306 for this infrastructure. And the next one is the rapidity, is how fast the system is going to bounce back. And in the interest of time, I'm going to skip through these. Again, we did the same analysis based on the time and duration of the rehabilitation impacts. We came up with the total probability for this rapidity aspect as 0.112. And then once we have that, the last assessment we did was sustainability after the impact. So again, after the impact, we know the materials that are needed to make this kind of reconstruction. That means there is reconstruction aspects, and again, the emissions that are going to come during this reconstruction are accounted for in this stage. And each one of these magnitudes are associated with the corresponding carbon emissions, embodied energy, and the fuel cost that associated with these construction activities. And this relates to the hazard-related sustainability has been normalized with the original sustainability numbers that we had, and the total hazard-related sustainability result was 87.43% for this particular infrastructure. And then the next step is to basically come up with these index numbers so that they can be plotted. The way we came up with the index numbers is all sustainability values are reported as $1 per year. Like I said in the beginning, we wanted to convert everything into $1 per year and use the fuel consumption as means to determine the cost per emissions. And this is, we use the U.S. Information Administration and numbers to convert the energy. So if we know the carbon emissions, then we can convert that carbon emissions to an equivalent fuel consumption using these numbers that are reported by Energy Information Administration. And that's how we came up with this $1 per year for the sustainability aspect. And for resiliency, we basically scaled it from -100 to +100, where each metric for the resiliency is scaled at between -20 to 20. So we basically gave equal weightage for each aspect of the resiliency. So 20, 20, 20, all of them add up to 100. And these values are scaled resiliency values basically by linear interpolation between these 20s. Okay. Then using these numbers, we came up with these values. So we normalized these costs, and we came up with a sustainability index for a summation of all the sustainability related costs, which is turned out to be 41 million. And the resiliency index value, which is a summation of all the R's, and this can this can range from -100 to +100, and this happened to be somewhere around 50, 49.9. And once we plot that, the next step is to be able to plot that information. And when we plot it, we see that this is falling in the green zone, which is very resilient and sustainable infrastructure. But there are several assumptions and drawbacks for this sort of analysis, because like I said, these are generic input values, which are actual construction input could come from on-site inspectors or feasibility studies. So if we had the real numbers, then these analysis will be more realistic. At this point, this analysis is mainly an exemplified one for earthen dam. And we also use the Bayesian statistics and the Bishop's method of slip slices. Again, there are several other methods to account for these probabilistic failure analysis and even the failure analysis for the slopes. And also, we didn't account for the spillway, which is which could be a weak zone in this dam, depending on how the spillway is being maintained and so on. So I just want to highlight the assumptions that we did, and also the drawbacks because of these assumptions that this analysis has been built on. So in conclusion, so we basically covered the importance of having a unified system for assessing the sustainability and resiliency, and having this accounting for the risk as an important aspect as well. And I provided an example, and also the future steps are to be able to start working with the decision makers, that means the owners or and also the practicing engineers, to make this framework more practical, more usable, because some of the steps that are involved sometimes are too in-depth and sometimes they are very superficial, depending on whether we have the data or not. So the future research is more in line with how we can make this more practical, so that it can be targeted. Maybe we need to come up with examples for different infrastructures, because right now we are only looking at earthen dams, but again, pavement infrastructure is another one which has different sets of input variables which need to be accounted for in this framework. But overall, this framework certainly has the ability to account for all these different variables and account for them in a manner that can be visualized to see which alternative is going to fall in what range within this sustainability and resiliency Cartesian plot. With that, I will see if there are any questions that came about. As expected, there were none. But one question I think that can come from for this analysis is the same similar question that I have been asking the other presenters as well. So what is the future? Like I said, the future is to make this framework more usable by practitioners and make it more practical. That's our goal towards this unified system. So in conclusion, I think this brings us to the end of this session, and I would like to thank the sponsor for this session, Keller, for sponsoring this event and leading the charge in ensuring that this sustainability in geotechnical engineering is becoming a practice. So with that, we conclude this session, and if you have any further questions, maybe you can reach out to us through emails or some other means through Geo-Institute. Thank you.